gonna welcome Anindya Day. He's a PhD and postdoc research at Johns Hopkins University, and gonna tell us about this visual transformer, this topic that Shatik kind of briefly dropped on a previous conversation. So welcome in.
Well, thanks to the organizers for having me. It's a pleasure to be at this meeting. It's really awesome how energetic people are. Give a rather pedagogical introduction to vision transformers. So I'm given to understand that there will be a part two of this talk, where I'll talk about the training part of the vision transformer. So for this talk, I'll mostly talk about the architecture and what self-attention does to the task of image classification in general. So just to begin with some background, so self-attention-based architectures, for which we use the generic term transformers, they have revolutionized the field of NLP ever since its paper in 2017. However, for computer vision, the dominant architecture still remains convolutional neural networks. And several attempts have been made to combine convolutional layers with self-attention layers in the past. But Vision Transformer, which came out in 2020, is a purely transformer-based architecture for image classification tasks. So that's where it kind of stands out from its predecessors. A generic transformer-based architecture has certain basic structures. Okay. So primarily, there's an input, obviously, and there's an embedding exercise that you need to do to break that input into a sequence of tokens. Okay. You can think of tokens as some vectors or tensors in some space, some vector space that's sitting out there, and you break your input into a sequence of tokens. Now, for LLMs, the large language models, these tokens are simply words. Now, once you have a sequence of tokens, the next step is to add some sort of a positional encoding to it to make sense of the sequence. I mean, in a sentence, words come in a certain sequence. Their order matters. So you need to put that information somewhere. And that is called positional encoding. And once you have that, then there are layers of attention, which maps as encoders and decoders and gives you some output. So that's the basic structure of any transformer-based architecture. Now, vision transformers work basically on the same broad logic. So let's look at the broad architecture of vision transformers. So it has three main modules: the embedding layer, the transformer encoder, and an NLP head. So the functional modules are all in gray. So it takes an image as an input, transforms it into a sequence of tokens. That's the function of the embedding layer. And then the transformer encoder acts on the sequence of tokens to produce a final sequence of tokens. Now, in this action of the transformer encoder, there is self-attention involved. So what self-attention does is that it makes the different tokens talk to each other. Okay. So, for example, if you're thinking of an LLM, a certain word in the sentence will learn about the other words in that sentence. Okay. And that's how it learns the language. And finally, you have an NLP head, which takes the sequence of tokens and gives you the logic for classification tasks. Okay, I'll pause here for questions or comments or clarifications.
You mean a sequence of token embeddings?
Say it again, what?
You mean a sequence of token embeddings?
Yeah. Okay. I mean, what do you mean?
Like it takes the image and converts it into a sequence of tokens or token embedding?
Well, it depends on what you mean by a token. By a token, I understand a vector or a tensor. So it's an embedding, if you will. So it's a sequence of vectors, a sequence of tensors. Yes.
Yeah. In language models, you have one-dimensional position. Now, you may still be doing this to the image, but there's also been argument for two-dimensional positioning.
Yeah, you could do that. Yes. Yeah, you could do that. Yes. I'll not hardcode that at all. Like, there are two ways of sort of philosophies of doing it. One is using the sinusoidal kind of positional encoding, and the other one is like using learnable encoding. And I'll go the learnable way, but I'll talk about that in a second. Okay, other questions, comments? All right, so then let's move on. But before we move on, the first question is, how do I even think of an image as a sequence of tokens? Sentence is clear, it's made up of words. What does it mean to think of an image as a sequence of tokens? So think of an image. It has a height, a width, and some number of color channels. Height and width are in pixels, obviously. So it's a 3D tensor of shape h times w times c. Okay. So this is Mona Lisa. It's 620 by 620, and there are 3 color channels. Okay. So how can I think of this image as a sentence? So the first step would be tokenization. So I'll reshape the 3D tensor into a 2D tensor. So how can I do that? I take the picture and I chop it out into patches of size p. So you can also do it with rectangular patching, but let's say they are all squares, they're p by p patches. So if I choose a patch size p, then the total number of such patches would be h divided by p times w divided by p. And each patch will have a total dimension of p squared times c. Now, to begin with, of course, each patch is also a 3D tensor, right? It has a width, it has a height, and it has a color channel. But what we are doing is that we are taking the patch and we're flattening. So which means that we're taking the 3D tensor and making it into a vector. Now, if I do that, then the dimension of that vector will be p squared times c. Okay? So, for example, if you take p equals to 124 in this case, the number of patches is 5 times 5, that's just 25. And the patch dimension is very large, 124 square times. Okay? Does this make sense, everyone? Yeah.
When you fly data, you lost the position information. So how do you handle that?
Say it again.
When you fly data,
yeah,
you change the tensor into one measure.
Yeah.
You will lose position information. Each pixel has spatial information.
No, we don't lose it. I haven't talked about it yet. I'll come to that. Yeah. So here I'm just here intuitively it's clear the order. We go like this, right? But that has to be coded somehow, and I'll come to that. That's indeed. Okay. So the point is that for a vision transformer, then a token is equal to a flattened patch. So that's what a token means. So that's, in other words, is a word in analyzing an image. So a word for an image is a flattened patch. So in this sense, you can have an image mapped to a sequence of tokens. Now, what does the embedding? So now, given that, I can sort of go back to this picture and try to understand what the embedding layer does. So I'll go I'll also go sequentially. I'll first discuss the embedding layer, the transformer encoder, and then the NLP. Okay. So now I can start with what the embedding layer does for us. So the first step is, of course, tokenization, which I just discussed. Usually, the tokenization is followed by a linear transformation, where each token. So remember that each token was a vector of dimension dp, right? So now you can perform a linear transformation and such that the tokens still don't talk to each other, but each token dimension is now dp, some d embedded. And then, since we will use this for classification tasks, we need to do something more. What we do is that we prepend these n tokens with a learnable class token of dimension d embedded. So basically, you had n tokens. I just put 1 in front. That's as a concatenation operation. All right. Now, why do I do that? The way this works is that I start with this combined token, including the class token, and let the attention layers act. And as I said, what happens in course of the attention map is that the different tokens start talking to each other, And in particular, the class token learns about the other tokens. So finally, what you have in the final setup, you have a class token that knows about the image. Okay. And then the idea is to isolate that class token and do some operation on it to isolate the logics and do the classification. Okay. So this is the logic of why we want to include a class token. We just have one more step before we actually. So there was a question about the positions of the patches. So now we're going to answer that question. So for that, you need to have positional encoding. So you add a learnable tensor of the same shape as the original sequence of tokens. So here, what this means is that you add token by token. So this is added to this, and so on. So the net shape of the final tensor is still the same. It's n+1 times dE. And so these are also learnable tokens in the sense that as you subject them to attention, they will also learn about the features of the image, and in particular, the sequence. You can also hard code it, but that's, we're not going to do that. It wasn't done in the original paper. So now, if you also include a batch index, because usually we'll have to we'll have some sort of a batch index. So now I've put it there. So it's a 3D index with the first index being batch, the second one being the token index, and the third one being the feature index. Okay, and this is the tensor that will feed into the transformer encoder. Let me pause here and for a second and see if there are
questions. Quick question.
Yeah, sure.
So you use learnable position for instead of side by side.
That's correct.
From better, or is because it explain?
So in the original paper, which I'm actually basically reviewing, mostly they use a learnable thing. I tried on small data sets, and I didn't see any particular preference one way or the other.
In terms of training time, does it affect?
Not much, but I only did like augmented evidence, basically. So so maybe for more complicated thing. But what they actually did in that paper was to check that if you have 2D sinusoidal embedding, positional encoding, then that does not improve your training speed or training accuracy. So it has to be 1D. Now, for 1D, whether you pick sinusoidal or learnable, that I don't. Okay, that has to be.
Do you use regular attention? Yeah, or use some kind of optimized fast attention?
No, I'll explicitly show what it's just normal self-attention. All right, so now we're in a position to discuss the next step, which is the transformer encoder. So we just described that there was a sequence of tokens that was being fed into the transformer encoder, and that acts on it and churns out another sequence of tokens of the same shape. So what is inside the transformer encoder are two main things. So there's the multi-head attention, and there is an MLP, which is just a fully connected neural network. So these are the two main submodules of the transformer encoder. So what happens is that the sequence of tokens are first subjected to some sort of a layer norm, which I'll describe in a second, which is then fed into the multi-headed attention. And the final output is via a skip connection or residual connection. So this input, so if you call this Z out, then Z out is Z out plus Z in. So standard residual connection. And then this acts on another layer norm, which leads to another MLP, and so on. Again, I'll skip. So I'll describe. I'll begin with the description of the layer norm, and then I'll discuss the attention and MLP. So is this picture clear to everyone? All right. So so layer norm. So I just mentioned that the input to the transformer encoder is a 3D tensor of that shape, D times N times the embedding. Now, what a layer norm does is that it does a normalization operation on the third dimension, which is the feature dimension. So what that means is that for a fixed batch index and for a fixed token index, so you pick a token, you pick a batch. And what you then do is that you compute mean and variance over the features. And then you normalize. And then you shift and rescale by parameters gamma I and beta I, which are learned. So they are very much like batch normalization, just that the index on which they are acting now are different. Okay, so if it were batch normalization, it would be like gamma A, blah, blah, blah. Here it's gamma I, so that's the. So it's interesting that how this is independent of the batch index and also the token index. So for all tokens, it's the same thing, and it's also across batches. So it's only in the feature direction that you're learning. Okay, so maybe in part 2 of the talk, I'll have more opportunity to talk about this because this has a interesting ramification. All right, so this is the layer norm, so it's clear. So now we come to the most important part, the attention block. So the attention is basically a nonlinear map, F hat, which maps the 3D tensor that I had written down to another 3D tensor, but of the same shape. So it's a nonlinear map, but it keeps the same shape. So to begin with, it was a b times n plus 1 DE, and it remains that. So there are several steps in this nonlinear map. So the first step is a linear transformation, which acts in this fashion. So the first is a linear transformation. So here you see that the last dimension, DE, is changed to a different dimension, 3 times D, right? So everything else remains the same. So it just means that you're taking the tokens and you're mapping them to a different vector space. That's all you're doing, just a linear transformation. Now, once you have done that, then you chop up the tensor into 3 different tensors, K, Q, and V. These go by the name of keys, queries, and values. I mean, the names are absolutely not important, but it's just a division of a tensor. And where the individual tensors are of this shape. Okay, so now these are the ingredients that you need for the self-attention map. So the self-attention map is given by this formula over here. So the softmax is being performed along the row of the tensor. I mean, you had both choices. You could do either row or column. So here the softmax is along the row. And the resultant tensor, capital Z, is also a 3D tensor, and it has a shape as shown. This b times n plus 1 times d. And then finally, there is another linear transformation, which puts it back in the original shape. So there's a linear transform, there's a self-attention map, and then another linear transform, so that the shape of the tensor remains the same. So this is, to answer your question, this is the attention. Now, in most cases, this is not enough. We need what is called a multi-headed self-attention. But that's a very easy generalization of what I just told you. The first step is still the same. You do a linear transformation, and you get a vector space whose dimension is 3 times capital D. But then what multi-headed attention does is that it divides D in this fashion. So NH is the number of heads, and DH is the dimension head. Okay, so you have now certain number of heads, and you have certain number of dimensions of those heads, which all add up to this capital D. And then you do the same sort of operation, the self-attention map, for each of the heads. And then you again put them together, and finally you get your tensor. Now the important thing, now this is like, okay, it's like algebra, but the important thing that one should appreciate is that the mixing of the tokens happen at the level of this softmax map. So the attention map is what mixes different tokens together. If you have linear transformation, then it's just mapping one token to another token of different dimension, but it's not really mixing the tokens together. So this is the stage where actually that is happening. Okay, so I'll just stop here for questions or comments.
What's the relationship between this capital D and DE, lowercase de,
Between what? Lowercase d and what?
and capital D?
Capital D. There is no relation per se. These are both hyperparameters for the model.
Is that same? Are they same?
They're not the same. They're not the same. They're not the same. They're different. So one is the embedding dimension, and the other one is sort of the internal dimension of the transformer. So they're different, and they're both hyperparameters of the model. So you will actually let the model know, and you will, if you optimize, then you'll optimize these as hyperparameters.
So do you know some typical values for this? Like what's in practice common for these, the ratio between these?
So, I mean, it depends. Sorry, what?
Attention usually has dimension 1, 500, 700.
Yeah, so it depends on what kind of VIT you're using. So there is like this base model for which I think the value is something of the order of 200 or 300, and there's a large.
512, like this is hard.
There's a large and there's a huge. So yeah, it goes increasing. So this is basically sort of, in some sense, you can think of it as a width of the network. So I mean, I'll talk about the depth in a second. But this is sort of the width of the network, the size of the matrix that you're dealing with at every step. So yeah, so it's a few hundreds basically. All right, so now there's an important thing that I should have mentioned earlier, but maybe this is a good time to say. So the transformer encoder, mind you, so this is like what is inside a single encoder, but there could be layers of such encoders, and usually you need multiple of them to actually do anything useful with your vision transformer. And so that's what this L is basically. So it's reminding you that there could be L such layers in principle, and this is called the depth of the network. So when you optimize, for example, your model, you optimize with the depth as well as the width. All right. So I discussed layer norm. I discussed multi-headed attention. So the one thing that's left is MLP. It's also it's also referred to as a feed-forward network in the literature. So it has a very simple structure. It has two linear layers, which is a GLU activation function in the middle. So note that the linear function's input dimension is DE, it's the same thing as before. And then there's an internal dimension DMLP, which is again a hyperparameter. I mean, that also you can fix. And then the final linear layer, which maps it from dimension DMLP to dimension DMLP. Okay. So at the end of the day, what the MLP is also doing is producing for you a nonlinear map, which maps the tensor Z to a tensor of the same shape. So it's still the same shape is being preserved. So we saw that first the attention preserves the shape, and now the MLP also preserves the shape. So that means that the full transformer encoder also preserves the shape, right? And since there are multiple layers of them, the full thing will also preserve the shape. So at the end of the day, what you have, what the transformer encoder is doing, is just producing a nonlinear map for you, which preserves shape of the 3D tensor.
Any particular reason to use GLU instead of ReLU activation?
Oh, it's why GLU instead of ReLU? I don't know. Maybe you have a better answer to that, but
I think if I recall that it has to do with just better smoothing of the gradient.
Yeah. So that's something that I kind of know that, So what GLU is it's proportional to, so suppose, let's call it fx, and its fx is x times some phi of x. So this phi is actually what is called a CDF for a Gaussian distribution, so the cumulative distribution. So what it means is that you're actually not looking at a density function, which is like local. You're actually using the information from like before up to that point. So it's usually a more stable activation function, but I don't know much beyond that. So also in various applications, like in physics, for example, you would get much better stability if you use a Gaussian. So it's probably related to those reasons. But fundamentally, I don't know why just GELU, or like why not some other combination? Like you could have ReLU and GELU. Okay, other questions. Okay, so then we can get to the final stage. So we have a tensor of this form. And what the final MLP head does is to basically just isolate the CLS token, which has by now learned all about the features of the image, and then just do this projection. So denum number of classes that you have in your classification test. And so what comes out are the logits. And so then you can do whatever you want with those logits. So this completes the classification test. So this is the functional description of this. Okay, so before I say more about attention, let me pause for questions. So just to sort of summarize what we did, we basically described in totality what this architecture looks like. So we basically discussed all the elements in this. So by now you should be sure of all the elements in this picture. If you are not, then you should ask me a question. Yeah.
Great presentation. Just a question. Do we run into the problem of exploding gradient or vanishing gradient with this problem?
Exploding gradient or vanishing gradient. I mean, that can happen in any training process, I guess. But what exactly do you mean? Can you say a little more?
So when we scan the full picture or whatever that Mona Lisa transformed into, so for example, when the attention head scans the ears, eyes, and then at the end of the picture, does it still remember all those eyes and ears are still important?
Oh, okay, yeah, I'll answer that question kind of in the next slide. It's not so much about what happens to the gradients, but it's how kind of attention, like what it does basically to a picture. Like how does it see a picture? So I'll kind of, yeah.
Yeah. So what is analogous to the masked word training in language?
Answer the question in just 1 second. Next slide is on that. Yeah.
Can I repeat it? I was asking, where's the analogy? In other words, when training a language model, you mask words.
Yeah, so I'll answer that. Okay. So then now that we understand the architecture, let's ask the question. So what the heck does attention do after all? Someone just asked that question. So for a given word, when the token is a word, what attention does is to help us focus on closely related words. Okay, so if there's a cat and there's a milk, hungry, maybe they will be related together, right? Now, for an image, attention does exactly the same thing. So it tries to build correlation through different patches globally on this 2D canvas. So this particular set of images are from the paper itself. So you can see that the input is that puppy, and after a few layers of attention, that's what it looks like. So what attention basically does is that it understands that the nose of the puppy is more important, the classification, than the grass. Okay. Yeah.
Another question. I'll just speak loud.
Yeah, please go ahead.
So what size are the patches typically? In other words, size of the dog's nose or the size of the dog's head?
No, so there's no, I mean, it's a hyperparameter. I mean, so which means that you have to.
What brain works? You can imagine that if it's too small, you're going to have problems.
That's correct. Yes. So there are two things. So if the patch size is sort of too small, then you have a large number of tokens, which means it's computationally very expensive for the transformer to work. So you have to sort of, you cannot make the patch size too small, and you cannot make the patch size too big either, because then it's not clear.
But that's why I asked, what practice is it? The nose, size of the nose is smaller, or the size?
No, I mean, I would say, in this case, yeah, I don't know exactly the figure of this, but
Isn't the patch size is some form of function of the resolution of the image as well?
No, so the resolution is like the full HD.
Yeah, I mean, like depending on the resolution of the
Yeah,
picture.
so yeah, definitely it will depend on that. So if it's an MNIST image, it's like 28 by 28. Like, what can you do? But I'm assuming that there's a pretty rich, subspace of image super space of image that you're looking at. So then I think it's not very clear like what is the right patch. It's like any hyperparameter like you need to train.
Yeah. I'm just trying to get an intuition for this. So, like in this example you give where it has the attention around the dog's head, is that because there's similarity between the different components of the dog's face and it's learned by looking at a lot of the images? So it's groups clustered them together.
That's correct, yes. Yeah, that's exactly right. Yeah. But it can do it for a variety of features. I mean, that is the kind of the new thing, right? I mean, so it actually is pretty nicely generalizable. Because if it were not, then it would kind of be not that. So this is a very nice graph from the paper. So basically, when it's like building these global patches, there is an integration of information across the entire image that's happening. Now you might think that you need to pass through several layers of transformer encoder to actually have this effective. But it turns out that that's not the case. It's a very weird thing. So what this plot is about is it plots the average size of the attended area. So the size of whatever the correlation is happening over the patches as a function of the number of layers. So one would think that when it starts out with neighboring layers, some neighboring patches, and as you increase the number of layers, you're actually going out in the wild. But what they showed in their paper is that that's not the case for all the heads. So what it does is that all these different colors are for different heads. So if you follow, for example, the green head, head 3, you see at a relatively early time, it goes all the way up to a very, very high distance. Okay? So it is not generically true that with increasing there is no large distance integration happening in the lowest layers. In fact, there are counterexamples. But what is true, as you can see in this asymptotic part of the graph, that tells you that at large depth, however, all the heads can probe large distances. So as you increase layers, slowly all the heads will be able to see the global correlation. So these are the pieces. Let me pause for questions. Yes.
So is that somehow related to the class token? Is it supposed to act like as a?
Sorry,
is that somehow connected to the class token, which is supposed to act like as a global attention token? So like this is kind of confirming that.
Related in the sense that yes, I mean you're doing the final analysis with the class token. So so everything that's happening as a result of self-attention is sort of being kind of put into the class token in some form or the other. So the class token is the only thing that has connection to all that has happened inside the encoder. Yes.
Right, yeah. So as the attention distance increases, that's kind of the class token.
That's right. So the class token knows more and more and more. Yes. Yeah. Exactly. Yes. That's correct. But the surprising thing is that even when the layers are like 1 or 2, the class token still seems to know a lot for some heads. That's like kind of weird thing, which you probably wouldn't expect.
Yeah. I'm just thinking, maybe it's not that weird because you think back a decade, the word that was like a single layer, and it still had similarity works well, learned similarity. Maybe it could be related to that.
Yeah, I don't know.
Yeah.
I don't know. It's possible that it's like how generic this behavior is has to be studied. I don't know like how generic this is. But the claim in this original paper, at least, that it happens, like it's generic enough for them to state this very clearly in their paper. But then there are also other kinds of, like you can also think of an audio file, an audio data as an image, right? They can ask the same questions. You can use a vision transformer to analyze that. Does this generalize to those as well? I don't know.
I also have a question. There's more in this plot than just the first depth. Like if you go to deeper depth, it like levels out at a certain distance, and it doesn't care anymore about the near pixels. Like, is there a reason for that?
It doesn't care for.
Yeah, it doesn't look at the nearest pixels anymore. At the closer pixels, it only looks at the further pixels. If I interpret this correctly.
Yeah, I have a feeling that they have actually left out certain dots over there just but because this cannot be so empty. But it's true that it will asymptote along us at a certain distance. There's some mean distance to which all the heads will basically asymptote, and this distance is that distance. But again, it's an average, so it will have yes. All right. So how am I doing on time? Okay, so now there is something that you probably have all heard about, VIT, that vision transformers. They all require large data sets. So this graph, this is also from the paper, and it basically tells you what that means. So here, BIT resonance are some sort of convolutional neural networks. I'm not going to go into the details of that. But just assume that there's some benchmark CNNs that are being compared with these VITs. So these shaded portions in the graph, this is where all the resonance lie. So this is where all the accuracies are. So you see that when the training is being done on ImageNet, which is the smallest data set of these three, then the resonance perform much better than the VITs. In fact, it doesn't even distinguish whether the VIT is large or like small. So here, large and small means like, again, the thing that you were referring to, like what is the width, what is the depth, blah, blah, blah. So they're almost universally bad with ImageNet. Now, when you go to ImageNet 21K, which is the next in size, you see that a lot of them are at par with the ResNet. And then, if you go to even bigger data set, the JFT, you see that some of the VITs are actually better than the ResNets. But what is also interesting is that the larger VITs actually start doing better. So the ones which have bigger depth, with bigger width, and generally larger number of parameters are actually doing much better. So this is basically behind this, folklore that that VITs need large data sets. So this is what it means. Yes.
So, my other question is: are these all trained from scratch when you're doing a comparison, or do you have some kind of patch tokenizer?
No, so they're trained on the data, and then they're evaluated on some data.
If you had a patch tokenizer that's already pre-trained, then you were just training for the attention, using it, it might work with smaller data sets because it would embed them, better. My question makes sense, sir.
But how would that, I can tokenize it, yes, but
no, I mean, so let's say, like you do with word tokenizer, you break them into tokens, and then each token gets put into its correct place in the vector space because that's been pre-trained. So when you're training this second model using the tokenizer, it doesn't have to learn the vector embeddings anymore. They're already, in a pre-trained model, which standardizes a lot of things. So you could have the same thing with the patches, where you have a patch to vec tokenizer or embedder.
It has to learn, right? I mean, it has to learn the features. I mean,
Well, you can already do that in from a previous model. Like you could have it learn the features. Yeah. It's not really, it's not really fine tuning. I mean, let's say you have a component that's been trained and it doesn't do attention. All it does is take a patch and output a vector. That's all it does. So say it's a dictionary of patches.
Okay.
And you train that. And then when you're now training your attention model, you now have predefined what the embeddings are going to be for the images as it's learning. So that's going to give it a head start.
That to me sounds pretty restricted. Like what? To me, that sounds pretty restricted. You can do that. That's a way of doing it. So that would be like if I have 5 hyperparameters in my theory, I don't want to artificially restrict 3 of them. Like if there's a good reason to do that, I'll do that. But why would I do that?
Well, they do this with language models, right?
No, I know, but I'm not sure how that intuition sort of maybe it could be true, but I don't see how that. I cannot see how that is sort of transferable to this.
I think that there's think of it in 2 stages. One is simply coming up with a vector embedding for a patch, and then the second phase of learning is learning the self-similarity and how the other patches around it affect it. And that could be much more involved and much deeper, but it would help you generate a small model because it would already have the advantage of having sort of a good.
I can see how that could work for certain tasks, but I don't know if that's generic. But we can discuss this.
Are you going to touch on the training objective? Are you going to touch on the training objective at all? Like the objective?
No, I'm not in this talk. Did you ask? Sorry, maybe I.
Can you say what the training objective is? Like, what are they like? So, I mean, for ImageNet, you'll basically trying to predict the class of the image.
One quick question.
Yeah. 2 questions actually. Yeah. 1 and 2. Yeah.
Sorry, it's kind of in line with the previous question. In the graph, we don't see Visual Transformer 14 in the first 2 bars. Is it because the data set was just too small to have some presentable?
So you see Vision Transformer?
The orange circle. It's not presented in the first 2 bars for ImageNet.
Yeah, it's just too bad, I guess. Yeah.
Data is just too small.
Yeah, because so that 14, 16, those are the patch sizes. Yeah. So it's a too small of a patch. Yeah. Or you can shout. That's not shouting.
Can you hear me now? Okay. So in a large language model, the size of the dictionary is limited because you only have so many words in a language. But in pictures, it looks like every picture is very clear, and it looks like the size of the dictionary is unlimited. So how does it affect the architectures that you use? Why the same architecture works for both texts and pictures with unlimited potential number of different patches, like tokens?
That's a great question. I guess in both cases, we're still working with some sort of performance. So, there's some things. There is certain value based on that thing. Similarly, when you're looking at images, there's also a purpose. You're looking at a set of images, and you're basically embedding things based on that set. But there's always a duplication of it, in which are embedded. So in that sense, it's similar. But obviously, the possibilities. So there's one difference. So in most the translation language have an importer and an export. But here you don't have just an import only. So it kind of takes away that part, which sort of depends on you have to have some. There are 2 spaces like English and Spanish. So you have enough embedding on both spaces for them to be able to talk to you. But here it's just a classification of here. No matter how big your set is, ultimately you're finally coming down to a much smaller set. So in that sense, it's could be thought of an easier task. Because it's mapping a big space to a much smaller. And that will be discrete. That answers your question. That's not my answer.
Actually, follow up to this question for myself. Do you think it makes sense to maybe use some convolutions to detect some like low-level features and then use tokenization on?
Yeah, people have done that actually. So there are dozens of vision transformers which basically do exactly that. So just to kind of orient ourselves, this is like a little experiment that you can do very easily to kind of basically buttress this point that VITs do need a large amount of data, and they don't perform very well when the amount of data is small to medium. So just take like augmented with endless data with some standard augmentations. I take a VIT with depth 6, so this is much smaller than the VITs that they are using. So most of the ones they're using have depth more than 10, like 12, 14, and so on. So here it's much smaller. And you take a very simple CNN with 3 convolutional layers. And you just run for 30 epochs, and you see that the VIT does extremely badly, even with augmented MNIST. So for after 30 epochs, it's like asymptotes. So it's indeed true, and there might be ways of improving this. So this is something that I'm gonna talk about. Next time. So let me. Okay, sorry. Sorry, was there a question? Okay, so I'll just conclude with the main takeaway points. So what I described is an encoder-only architecture, which does classification tasks in computer vision, and we discussed the different parts. Now there are several possible tweaks to the architecture, as Vlad was pointing out. You can try to couple them with convolutional layers and so on and so forth. But there's a easier sort of tweak where you can think of replacing the layer norms with the batch norms. And we know from the history of CNNs how the introduction of batch norms actually, caused a mini revolution in that field. And it's an interesting question whether one can integrate batch norm in the architecture of VITs. And I believe I'm going to talk a little bit about this in the part 2 of the talk. Not today. And the second important thing is the role of attention in understanding global patterns of the images, which I alluded to earlier. And last but not the least, thank you for your attention.
Thank you. Well, yeah, wow, that was very interesting. Thanks so much. And I think we're gonna do a few questions. Yeah, few more questions.
In that last graph was the CNN versus VAT comparison. Is it comparing models with the same number of parameters?
Roughly, not exactly, but roughly, same order. Also, roughly the same GPU.
Any more questions here? You'll still have chance to ask Anindya after the event. We're gonna hang out here for probably like 15, 20 minutes, and then we're gonna go to the bar to celebrate the start of their season. And I'll put the QR code for the Google being on the screen shortly, and we're gonna meet you there, whoever want to join them. So thank you, and yeah, we'll see you next month otherwise.